Okay, continuing on 1.6, something called the squeeze theorem. Now, the squeeze theorem is not a big deal. It's not a huge deal in this thing, but the squeeze theorem will allow us to do something, and that something will allow us to do something else. And I don't want to get into it, but well, the squeeze theorem will allow us to find other limits. Now, when we learn the squeeze theorem, you're going to go, well, that makes perfect sense. Matter of fact, this theorem is so obvious on a certain level that you're like, what's the point? I'm going to try, if I can, to illustrate why it's not as obvious as it might appear. But if you kind of just let it flow over you, you're like, oh, wow, this is really stupid. It's so obviously true. That being said, I'm going to try to show you why we make a big deal about it, okay? But don't panic. This is super simple, okay? And the idea is simple. Actually doing a proof of this theorem is complicated and all, but and I'm going to try to show you why it's a weird theorem in a little bit, okay? So here's the deal. The squeeze theorem says this, and this is it. Suppose you have a function f, we'll call it f or blue, and it's always bigger than a g function and always less than the h function. So just to draw it real quick. So, and then we're going to have some point A that's going to be kind of important to us here. So we put that here, and then it goes to some point L here. Okay, so suppose I have some g function. La, 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 there's my g. There's my g function, okay? But g is the smallest one. It's like the littlest pig or something like that. And then there's the h function. H function is always bigger than g. And then here's the deal. The f function, it has to live in a world between g and h. Now it can actually touch g or touch h, but it's always got to stay, oh my God. And again, if you're looking at the conclusion here, you're like, it's really that obvious. It's really that obvious. If I know the little g function has to go through has a limit of L at A, and I know that h, the big function, has a limit at A, and f is always between them, what can I conclude? Well, the limit, and I know this is just earth-shattering. Well, it's not really earth-shattering because it seems dreadfully obvious. I want to talk about why it seems so obvious. Well, if f is always between g and h, or equal to, but g has a limit of L at A and h has a limit of L at A, I can conclude that f has to go. Okay. It's that simple. Now, here's the thing. It works for limits, not just function values. And that's the key. I drew a perfectly nice continuous function, so remember we didn't have any of those weird breaks or holes in the function, right? So let me see if I can do an example tonight, right now, of why that is important. Now, I'm going to try using the graphing calculator, which may be hard to see, but don't panic if you can't see it. I'm going to try to draw over it and make it as clear as possible, okay? So don't panic. And this is just more to give you it seems so obvious. Why is it not as obvious as it might appear? And it has to do with the idea of a limit, right? We drew a limit where it was also continuous. And then it's pretty obvious. But don't worry, it's still pretty obvious. Okay, so let me just do a homework-ish question here. Suppose I want to find the limit of x times sine 1 over x. Now, what you may not realize is this is a wacky function. Not normally, but around 0, okay? Think about it. Sine of 1 over x. Remember, 1 divided by a tiny number, like 1 divided by 1/10 is 10. 1 divided by 1/100th is 100. 1 divided by 1/1,000,000th is 1,000,000, right? So here's the weird thing. We're trying to figure out what the sign is going to be if x is going to 0. Oh, You know what, for the sake of this question, can we make going just from the positive side? I'll explain why. It's not a big deal, but it would be mathematically wrong to do both sides at once. So let's just do one side at a time. So let's just do this right here, okay? So what we're gonna do is we're gonna only let x be bigger than 0 for the sake of this question. Okay? Now, here's the deal. What would that limit be? Okay? Well, you could use some common sense, and that will work every time on these suckers, okay? But when you're doing your homework, you want to actually do it in proof format, okay? Okay, the common sense. What do you know about sine? What I know about sine, and this is kind of what we're going to do. Sine is some number between -1 and 1, right? The sine, just from trig, we know is between -1 and 1. So I don't even care what's behind my hand, right? I just don't care what's there. As long as the sign exists, it's going to be between -1 and 1, right? Right? It's going to be between -1 and 1. Okay? Let's look at what's happening there, okay? Let's look what's happening there. Now, this may not work well because I haven't tried this yet, okay? This is like, oh, this is like a pandemic thing, right? Normally I would use what's called my graphing calculator here to, hold on, let me just see if this works here. Window, sine, so there it is. If you can't read it, it's x sine 1 over x. So let's just graph it and hopefully see. Now, we're doing this around 0, so what I'm going to do is I'm going to make my window ridiculously small, okay? My window, again, if you can't read it, I'll read it off to you. 0.01, 1/100th, negative, 1/100th positive, 1/100th negative, 1/100th positive. Because, remember I said before, there's all sorts of weird, does not exist? This does not exist. You can't put 1 over 0 in, right? You can't divide by 0. But what's happening there, it's not going to infinity, okay? But let's talk about what's happening. We have to talk about that in a minute. We'll do it philosophically, though. Let me do the graph here. Oh, crap. X. Okay, this thing's not working. Will you watch the graph? It's spazzing out, right? It's spazzing out. Now we're only going to look on this half, so let me just kind of like, it's doing weird crap, like blah, blah, okay? But what we notice, again, we're going to come up with the answer first, and then we'll prove it in a second. What we'll notice, if we look at that, is I'm going to put x and negative x in, and I'll explain why in a minute. So again, it's spazzing out, right? It's behaving very weirdly. It's like, and I'm going to explain why it's spazzing out. It's spazzing out, but it's coming down now, and then it spazzes out going out off the other end, right? Spazzing out, and then but here's at y equals x, and then here's y equals negative x. Notice that even if it's spazzy, it's still between x and negative x. So we can arrive at the fact that even though it's spazzing out, it's got to go through 0. Okay? Now that's not the proof. Okay? That's not the proof. Let me turn this off here. Okay? That's not the proof. Let me put the axis on just for the fun of it. But that's kind of a cool explanation. And actually, we're going to kind of prove it using that idea. I've lost the top to this black pen, so I'm just going to set that to the side for the moment. Okay, so here's what we're going to say. This sine piece is the problem. Let me stop and say this really categorically here. Let me be as clear as possible about this. When do you need to use the squeeze theorem in your thought process? When you have a function that's bizarro. That function is bizarro because it's going out to infinity. What's the sign at infinity? Well, here's the thing, right? Up to 1, down to -1, up to 1, down to -1, up to 1, down to -1. What's it doing when it gets out to infinity? It's going up to negative 1, down. So here's what we say. It's approaching every number between negative 1 and 1 equally at infinity. That's weird, right? Like at infinity, the sign of infinity is some number between negative 1 and 1. You can think of it as approaching all numbers equally. So we say the limit, it does not exist. So that doesn't exist, right? But here's something we can do. This is what's called the squeeze theorem. So we can't really do this part, right? We can't, oh, sorry. I went off screen there. We can't, F. So here's the deal. When do we use squeeze theorem? When we have a really weird function for F. When we have a really weird function for F. Or we don't know what F is at all. Like we don't know what F is. But we can do this. I know that it's trapped between negative 1 and 1. So watch what I'm going to do. I'm going to say, well, I know the limit of x sine, and we already know the answer is 0, okay? But let's just go through the mathematical explanation. Here's what we're going to say. We're going to say, well, I know that the most that can be, or least, is negative 1. Crap, sorry. I circled the wrong thing, guys. The most that least sine is negative 1. And at the most, I forgot that x equals 0 here. At the most, so I have negative x on this side and x, at the most that is 1. So what I'm going to do is I'm going to put the negative 1 in for here, and then I'm going to put a positive 1 over here. And then obviously, if I put 0 in here, I get zeros on these ends, right? You know, if x approaches 0, what does x approach? Duh, if x approaches 0, x approaches 0, right? And then, so I can conclude that this is, by the squeeze theorem is trapped between them, right? So this has to be 0. Now again, if the function makes sense, like f makes sense, this is so obviously true. When do we use this? When we don't know what f is, but we know it's trapped between two functions, or when f is so bizarre we don't know what it is in a different sense, like it's just crazy weird, and that's what's going on there. So that's called the squeeze theorem. Now, I did need to stop. The squeeze theorem allows us to do. Let me just end this with why we would need this. We need the squeeze theorem to technically do this limit. Don't worry, we're not going to do this one right yet. To prove that that's 1. And then that will do something called a derivative. It'll prove that the derivative, and now again, everything in blue here is not known to you at this point. But in calculus, all calculus, it was called differential calculus, which stands for derivatives. It's like everything we're going to do. But so we're learning about the squeeze theorem now because it's technically a limit question, but we're not going to need it till like next quarter, okay? And then I'll refer back to it in a weird way. So just be aware of that, okay? Anyways, squeeze theorem, pretty obvious idea. If you can trap a function between two, and again, the idea is this. Suppose f is some weird function. I don't know what this is. Oh, see, this is the one that died, right? Throw it away. Bah, it's gone. Okay, I don't know what it is, but I can trap it between two known functions. Then I can actually, and I know these two known functions go someplace, then I know that this function would have to go between it. That's all that it said. It's not that big of a deal. Probably not worth the time we spend on it, but because we're going to need it in a couple steps later, we just kind of make sure we cover it, okay? Okay, thanks.